All right, today we're diving into a quest to find the perfect tool for one of the most critical jobs out there, storing and retrieving data as fast as humanly possible. In the world of high stakes apps, picking the right data structure isn't just some homework problem. It's the real difference between a user experience that feels instant and one that's just infuriating. So, picture this. You're building the next big thing. You've got millions of users. When someone logs in, they want their profile to just appear. They're not going to wait around while your system digs through mountains of data. And that's our core challenge, right? How do we build for speed when we're dealing with massive scale?
Our journey starts with the most fundamental tool in the entire toolkit, the one we all learn on day one, the array. It's our baseline, it's our starting point, and it's beautifully simple. But the real question is it fast enough for our mission?
I want you to think of an array like a perfectly organized street of mailboxes. Every single box has a unique number, its index. And if you know that number, say box number 1337, you can walk straight to it. No peeking in any other boxes. This direct access, that's the array's superpower. See, because an array is just one solid continuous block in your computer's memory, grabbing an element by its index is lightning fast. We call this O of 1, or constant time. And that means it doesn't matter if the array has 10 items or 10 million. The time it takes to get to item number 500 is exactly the same. But try to insert an item in the middle? Whoa, you have to shift everything after it, and that is painfully slow. And right here, we hit our first huge roadblock. What if you're looking for a user named Alex, but you have no idea what their index number is? Well, you've got no choice. You have to start at mailbox 0 and check every single one by one, until you find them. This is a linear search, or O of n, and for our app with millions of users, it's an absolute disaster. So this brings us to the big question. Can we get that amazing direct access speed without needing to know a numerical index first? There has to be a better way, right? Well, thankfully, the answer is a big yes. So, enter our second contender, the hash table. This thing is often talked about like it's some kind of magic black box that just gives you what you want, almost instantly. So let's pull back the curtain and see exactly how this trick works. Imagine checking your code at a busy restaurant. You give your name, Alex, and the host uses this special rule. We call it a hash function that instantly tells them your coat is on rack number 7. They don't search all the racks. They go directly to number 7. That right there is the core idea of a hash table. So instead of a numerical index, a hash table uses a key, like a username, to store a value, like all that user's data. A hash function magically turns that key into an array index. And the result? On average, searching, inserting, and deleting are all O of 1. It feels like we found the perfect solution. But hang on, if you're ever in a technical interview, this is where you really shine. What happens if that special rule tells the host to put both Alex's coat and Sarah's coat on rack number 7? That's what we call a collision, and how you handle those collisions is absolutely critical to a hash table's performance. And there's the catch. The magic has a weakness. If you have a bad hash function, or you're just really unlucky, a ton of keys could all point to the same index. Your single rack now has a huge line of coats. And finding someone's coat in that line means, yep, you guessed it, checking each one by one. We're right back to that slow, painful O of n search. The magic has another big limitation too. That hash function, it scatters data all over the place. That's what makes it so fast for lookups, but it means there's zero sense of order. You can't just ask a hash table for all the users with names between A and C. For that kind of thing, we need a structure that's built on order itself. And that leads us to our final challenger, the binary search tree, or BST for short. This structure's entire reason for being is to maintain order. It gives us a really elegant solution for when the sequence and relationship between our data actually matters. A BST works just like a game of 20 questions. You start at the very top, the root, and you make a simple decision. Is the user I'm looking for alphabetically before or after this one? If it's before, you go left. If it's after, you go right. With every single step, you chop the number of remaining possibilities in half. This super simple left is less, right is more rule means the tree is always sorted. And that gives us some really powerful abilities, like instantly finding the smallest or largest value, or getting all the items in a specific range. In a nice, well-behaved, balanced tree, All these things take O log n time. It's not quite the O of 1 of a hash table, but it is dramatically faster than O of n. Okay, you're probably sensing a pattern by now, right? Every single one of these data structures seems to have a secret weakness, a worst-case scenario. And for the BST, that weakness is a really, really big one. So what happens if you insert data that's already sorted? Say A, then B, then C, then D. Well, the tree stops being all bushy and balanced. It actually degenerates into a long, crooked chain. Your super efficient decision tree is now just a glorified list, and searching it is, once again, that slow ON slog. And here is your second interview gem. The fix for this problem is to use a special kind of BST that balances itself automatically as you add things. These are things like AVL trees or red-black trees. They do these clever little rotations to make sure the tree never gets too lopsided, and that guarantees you that sweet O log n performance. Okay, we've met our 3 contenders, we've seen their amazing strengths, and we've uncovered their secret weaknesses. So now it is time to put them side by side and see how they really stack up in a direct comparison. This table just lays it all out so clearly. Look at that search by key row. The hash table's O of 1 is the undisputed champion for raw lookup speed. But look at range query. The BST is the only structure that's actually designed for it. And for just pure access by a number in index, nothing can beat the array's O of 1. See, there's no single best tool, only the best tool for the job you're trying to do. So let's just bust a common myth right now. People love to say hash tables are O of 1, period. But the reality is a little more complicated. That's the expected time. The worst case, which is totally driven by those collisions we talked about, is O of n. Real-world performance is all about managing that risk with a good design. And on the flip side, you might hear people dismiss BSTs as being slow. And yeah, O log n is technically slower than O of 1, but a balanced BST offers something a hash table can't, a guarantee of performance. Plus, it unlocks a whole world of order-based things that hash tables just can't do. Okay, now that we've gone through all the theory, let's just boil it all down into a practical guide. How do you make the right choice? You know, choosing the right structure really just comes down to one key question. What's the main thing you're going to be doing? If it's access by number, use an array. It's a no-brainer. If you need the absolute fastest lookup by a key and you don't care about order, you go with a hash table. And if your entire application depends on keeping things sorted or finding ranges of data, a balanced BST is your best friend. Ultimately, it all comes down to this fundamental choice between 3 priorities: direct indexing, pure lookup speed, or powerful ordering. There's no single right answer for everything. There's only the right answer for your specific problem. So which one does your next project need most?